Okay, so it's our great pleasure to have Zulaihat Hassan, who is currently a PhD student at Auburn, and she will graduate this year, I think. Um, she will give a talk on chemotaxis models with nonlinear porous-medium diffusion, consumption, and logistic source on RN in the Mitake Trend seminar. So please, Zulaihat.
Thank you so much for the introduction. So this is a joint work with my PhD advisors at Auburn University, Dr. Shane and Dr. Paul. So first of all, here is the outline of my talk. I have the introduction. Then I'll talk about our result on global existence of weak solutions. And then if time permits, I will also talk about asymptotic behavior of solutions in for regular diffusion case and some remarks and future work. Okay, so first of all, what is chemotaxis? Chemotaxis refer to the ability of living organisms to react to some chemical signals in their environment by either moving towards area of high concentration gradients of these chemical signals or by moving away from them. So when they move towards the chemical signals, we call that case chemoattractant, which is what I try to depict with this animation here. These are like the mobile species, and the blue ovals are like the chemical substance, and the species are being attracted towards this chemical substance. Both the species and the chemicals kind of diffusers move in the environment. And a situation where the chemical substance repel is called the negative taxis or chemorepellent. Chemotaxis plays a central role in many biological processes, for instance, in cancer metastasis, where organ-specific stroma cells releases signaling proteins that induces chemotaxis and attracts cancer cells. This kind of means that if we are able to address this chemotactic pathway, it could offer promising avenues for preventing cancer metastasis and improving the cancer outcomes. There are also other applications of chemotaxis. For instance, we have applications in marine animal fertilizations, in immune responses, and also in bone healing. Mathematical models of chemotaxis date back to the work of Patlack in 1950s and Keller and Segal in the 70s. And since then, there have been several variants that has been studied in literatures. In this talk, um, I will be talking about this system, this chemotaxis model. So they introduce this as a system of PDE. The U here represent the density of the mobile species, while the V represent the density of the chemical substance. The first term here represents the internal diffusion for the mobile species. M here could be any real number, but in this talk we focus on when M is bigger than or equal to 1. If M is greater than 1, strictly greater than 1, this equation becomes degenerate and is of the porous medium type. While for M equal to 1, that is the regular diffusion case. The second term here models the chemotaxis sensitivity, and this is a case of where we have linear sensitivity. Chi here is also any real number, is a constant, and when it's positive, it models when we have chemoattractant, and negative represents a chemorepellent. This term here models the effect of local dynamics of the mobile species. A and B here, and this is the logistic source that we have. A and B can be negative. If A and B are 0, this system is called the minimal chemotaxis model. And when A B positive, that is when we have the logistic source. Well, for the V equation, the first term is for the diffusion of the chemical substance. This term here means that U has a negative effect on V. As such, we call this case it's modeled the case where we have consumption. The domain here, omega, can be bounded or unbounded, and whenever it's bounded, it's often studied with the homogeneous Newman boundary condition. In this talk, I'll be talking about global existence and uniqueness of this chemotaxis system in the whole of Rn. That is, omega in my case is the whole of Rn. And I'll also talk about the existence of classical solution in the regular diffusion case when M is 1. And so why do we want to why do we study this model for porous medium kind of diffusion? So notice that the diffusion term can be written in this form, and diffusion coefficient is now m times u power m minus 1. Now, classical linear diffusion assumes that movement is like standard Brownian motion, that is, the spreading rate is constant independent of density. However, in many real biological situations, such as in tumor growth, dense tumor core generate pressure-like effects that drive outward spreading. This diffusion here is better modeled with the porous medium type diffusion. And also, one other properties of the porous medium diffusion is that it has finite speed of propagation, unlike the case of regular diffusion where we have infinite speed of propagation, which is not realistic biologically. Now, given any chemotaxis model, what are the central problems we ask? We ask question of first, well-posedness. So do we have local existence of solution that is, given any initial, can we find a solution to our chemotaxis model that satisfies this system in some sense, in some maximal interval? And if we can find a solution in some interval, does the solution exist for all time? That is this Tmax finite or infinity? And if Tmax is infinity, is the solution uniformly bounded for all time? And also we ask question on asymptotic property of this solution. So we ask question on like existence of special solutions such as the steady state solution, or when we are on the whole of Rn, we can ask question on like existence of traveling wave solution. And also we ask question on whether the solution does converge asymptotically to any of the special solution as time goes on. And of course, one very interesting question is how does chemotaxis sensitivity affect the dynamics of the dynamics behavior of the mobile species and so on. So like I said, my talk is focused on the chemotaxis model, porous medium diffusion and logistic source and consumption in the whole of Rn. So I want to point out some of the known results on this model in the case of when the domain is bounded. So first of all, we are like the first to study this model when in the regular diffusion case and for any dimension in the whole of when omega is the whole of Rn. So in bounded domain, so some of the, I just want to point out some results. For the case of regular diffusion, it was proved by Lee in 2015 that we have existence of globally bounded, existence and uniqueness of a globally bounded classical solution in 1 and 2 dimension without any condition on the constant. While when the dimension is bigger or equal to 3, Tao in 2011 studied this model, Wang et al. In 2013, Wang et al. Wang in 2017. They studied this model and existence of globally bounded classical solution under the assumptions that the norm of the initial for V and absolute value of the sensitivity constant, kappa is small. Very recently in 2025, Langett and Winkler studied this model when A and B are 0 and proved the existence of global weak solution without this, they removed the smallest assumption. And they show that this weak solution can become classical after some time, though they didn't answer the question on uniqueness in this case without the smallest assumption. Now, in the case of the general diffusion, that is when m is bigger than 1, Wang in 2016 proved that for minimal chemotaxis model, when m is bigger than this number, we have global existence of globally bounded weak solution. And with logistics source joined in 2017 and 2021, studied this model in 3 dimensions and prove existence of globally bounded weak solution. All right, so like I said, we're studying our model in the whole of RN, and one of the reasons, one motivation for studying on RN is that in real life, we can have the domain is really large. So how do we model such scenarios? And it can help us to study the model from other perspective, to study the behavior of the especially from other perspective, for instance, from perspective of whether it does chemotaxis does slow down or accelerate the invasion of the population. Now, studying this model on RN poses some kind of some challenges. So, for instance, in the case of global existence, in studying the global existence, in bounded domain, usually to prove that the solution stay bounded, they prove that they use energy method to prove that LP to establish LP bound of the solution, and then use the Moser iteration technique to upgrade the LP bound to L infinity bound. And now, but on our end, the solution might not be integrable. It might not be in LP. So the LP norm may not be finite in that case. So how do we handle that situation? Also, for bounded domain, we can treat both integrable and non-integrable initials in the same manner, since bounded functions are also integrable in bounded domain, but that is not the case on Rn. So we have to study this model for when the initials is integrable and non-integrable, like separately. Also, for the case of regular diffusion, that's when M is 1. If we're on bounded domain, when the solution is positive somewhere, then in fact the inf stay positive. Well, if in an unbounded domain, the solution will be positive at any given time, but the inf can be 0. This poses like some challenges when studying asymptotic property. All right, so now on the global existence of weak solution. So I just put in here what we mean by a weak solution. So a weak solution of our equation on the whole of Rn, and this is for when m is bigger than 1. So we let m be bigger than 1, say positive, u0 in L infinity, v0 in W1 infinity. So let me point out that for this allows our initials to be non-integrable. And kind of why we need to non-integrable initial, because it will lay some foundation when studying the asymptotic property. So we said a pair UV is of non-negative functions. It's called a weak solutions. And our U0, V0 also assumed to be non-negative. If it's satisfied that U, the gradient U per M, U greater than V are in this space, and V is also bounded in this sense. And for every continuously differentiable test function, we kind of have integration by parts formula satisfied, which is like roughly the usual sense of weak solution. So here is our first main result. So this is our standing assumption. M is bigger than 1, U0 L infinity, V0 W infinity, U0 V0 non-negative. So we show that we can find a non-negative weak solution of our systems that satisfy first the local LP property for any p bigger or equal to m. For each time in 0t and p bigger or equal to m, u of t is locally in LP plus 1 of Rn, and exponential minus t over 2 gradient u power p plus m over 2 is locally in L2 of the space. And also we have the L infinity estimate that is, we can get a constant positive. This constant here is independent of time, t, such that both W1 infinity norm of V and L infinity norm of U is bounded. Our constant in these two estimates only depend on the constants and the norm of the initials. So the constant in the system, that's like the A, B, the kappa, and also could depend on M. Then we'll also have that this solution is also Holder continuous in the interior. And moreover, if our initial is Holder continuous, then the Holder continuity hold up to the initial. Now, for this system, Holder continuity is like the highest regularity we expect, since even the porous-medium equation the is only Holder continuous. Like the fundamental solution is just Lipschitz continuous. So we expect that in this class of regular solution, we should have uniqueness. And what we prove is that if we have V0C alpha and V0C2 plus alpha, if B is positive, then we have uniqueness when M is between 1 and 3. And if we don't have logistics, or like if B is 0, then we have uniqueness for any M bigger than 1. And so our existence result is for when A, B are positive. So we said we have uniqueness in this class of Holder continuous when M is between 1 and 3 for B positive, and for B equal to 0, we have uniqueness for any M bigger than 1. Okay, so because our initials are non-integrable, this is like the kind of first work that was done for non-integrable initials, existence of weak solution for this kind of system for non-integrable initials. And so I want to give an idea of how we prove our theorem on global existence. So to prove the global existence, first of all, we consider the top problem of our equation given by this system. And we show that for this system, we have when the initial is kind of smooth enough, V0 epsilon C1 plus alpha, V0 epsilon C2 plus alpha, for any n bigger than 1, this system has a classical solution that satisfy all the properties of our equation independent of epsilon. So that when we take limits as epsilon goes to 0, we can use compactness argument plus this uniform estimate to now establish existence of globally bounded weak solution as a limit of this classical solution. So the idea of proof now is I'm gonna give how we come about the LP estimate and the norm-infinity estimate for our equation for the top problem. So we assume kind of we have a classical solution and we can do a lot of things. Uh, so again, in our theorem, we have local LP estimates. So how do we get local LP estimates without introducing any boundary condition? Instead of getting the LP bound for U, we multiply by a cutoff function, like an exponential decay cutoff function, that satisfies some kind of nice property that helps us. So like we want this cutoff function to have this decay property, of course, and then we want it to satisfy some form of like Hanach inequality, that is, in this world we can compare the psi at any point. And of course, we want it to have like some kind of, we want to have a control over the volume. So we want this integral and this to be bounded. Okay, so with that kind of cutoff function, we start by multiplying our U equation by UP times psi squared. Psi here is our cutoff function. And then we have the derivative of this integral can be controlled by this term. So the local LP bound, to get the bound, it's enough to control each of the terms. So let me mention here that we have P plus 1 here and psi squared here only for convenience. So it can just be psi and UP. Now, because we introduced this cutoff function, kind of it's introduced some extra terms, or like some terms that are really difficult to control, like the terms in red. So I'm gonna explain how we control each of these terms using a property of the property of the test function. So we'll note that this is from the diffusion term. This term is good. I1 is good. Now I2 by Young's inequality can be controlled by the diffusion term and now some problem term. So this term is a problem because when M is big, we cannot easily control this term alone by just so here I also have a good term, which is the logistic source. So, but when M is big, I cannot easily control this by just the logistic source. And we had to use all the favorite and both the logistics source, the diffusion term, and the regularity of our initials in order to control just this term. Okay, so I'll explain this later. So first, we can easily control I2 this way. I3 is good because of this gradient psi. We can control I3 by the diffusion term and sometimes involving gradient V. I4 also can be controlled in this way by the diffusion term, the logistic source, sometimes involving the gradient of V and a large constant. And I5, of course, I said is a good term. That's a logistics term, can be controlled in this way. And we actually just needed this term in order to kind of bound independent of time. So putting all of this inequality together, then we can bound
Can I
the,
ask a quick question on the previous one?
yes,
Just
please.
very quick. Yeah. So, as you said, that is a very bad term. If m is less than 2, then is it readily bounded
Yes,
by the
if M is less
logistics
than
term?
2, yes, it is bounded by the logistics source. And that's why I said this term is problem if M is big. So if M is
Okay.
bigger than
Yeah.
that's where we have
Thank you.
problem.
Yeah. Great.
M
Yeah.
is less
Thanks.
than 2, kind of we can control this term we can control it by the logistic term and everything becomes nice. Yeah, thank you. All right, so when we put those terms together, we now have this estimate that the derivative can be bounded. These are the good terms. That's the diffusion term. So here, sorry, this should be less or equal to the constant here. See, they are like universal constant, and they could depend on all they only depend on like A, B, kappa, and are independent of epsilon and time. So we have this inequality now. So first I will start with this bad term here. First, we use Gagliardo-Nerang inequality together with like some LP interpolation inequality to show that we can bound this by this term here, which is related to the diffusion term, plus some other term. Now, when you look at this new term, we have p plus m over 2. P is bigger than, so this is fine. But we have psi here has a power q star. Q star is just a number between 1 and 2. Now, all other terms that we need to compare them with have power 2. So first, we need to use all the properties of our psi, which is like the Hanach inequality, the fact that we can cover the whole of Rn by some balls, to show now that we can control this term by some constants that times roughly the logistic source and a B constant. This is kind of the reason we needed most of the properties for our kind of function. Now, when we put those terms together, we can control this by this term, which roughly is like the diffusion term plus our logistic source to some power and a large constant. And now we put those together. We have this term here. And how do we control the V? To control the V, we first of all multiply our equation on both sides by exponential s, and then integrate in time so that we have this inequality here. And then we apply some interpolation inequality because this time here when this is because we have this 2 times p plus 2. We want to be able to control this by roughly the logistics source alone. So we use like interpolation to bound this by like the second derivative and then use like maximal regularity, maximal regularity estimate on the v times equation satisfied by v times psi squared plus the property of psi, then we can roughly control the v. We can control this term here by some delta times the logistic source and a large constant. And that is how we deal with this term. Then we can put everything together. The logistic source can be controlled here, and we have a much cleaner estimate. So we have like the LP plus 1 and this is the diffusion term. We just did not put the logistic term and can be controlled by this in this way. Where what we did actually, we take the supremum in X naught, and then we let YP plus 1 be the sup. So this is roughly like the LP plus 1 um, norm of U, a local norm of U. Now, how do we deal with this power that we have here? We use some kind of continuity argument. So we said if we start, or if we choose, because our initial is bounded, so, and the property of psi, if we choose C big enough such that at initial we can control it by C times kappa power minus n, then the local LP plus 1 at any time is at most 2 times this number. So we use a kind of, we prove by contradiction, and that the YP plus 1 is at most these 2 times this number. And this constant here is independent of time, independent of epsilon. And that is how we got our local LP bound for our U. Now, if you look at the V equation, sorry, here, the V equation here have a formula. We can use like the semi-group property to write it out. And then we use semi-group theory to show that if you have a local LP bound for U, it implies the gradient V norm infinity is bounded. Now, using the fact that the gradient V norm infinity is bounded back in our equation for U, then we apply like a Moser iteration technique to upgrade from that to norm infinity bound. And that is how we prove our properties for the put-up problem. We got the bound independent of epsilon, we take limit, and then we have a globally bounded weak solution for non-integrable initials. Um, so that is for the case of when m is bigger than 1. When m equal to 1, which is a regular diffusion, the equation, the LP estimate is much easier to control. In fact, we don't have the bad term in that case. So like you said, when m is 1 or 2, that term can be controlled by the logistics, so we don't have that term. So, but what we have here is now this term here, we cannot control it because we have like a constant here, a constant here. We can only control this by some constant times the logistic source in this case. And so for the case of regular diffusion, for now, we're only able to have global existence of globally bounded classical solution under condition that the logistic term is big enough. So that's chi absolute value of chi times the L infinity norm of initial is small. That is kind of roughly how we have this condition for now. So for the case of when m equal to 1, we have more than weak solution. In fact, we prove in our first work publication JDE 2024 that for U0 C be uniform, V0 C1 be uniform, or U0 integrable, and V0 W1 Q big enough, this problem has a unique classical solution on some maximal interval, and this interval is infinity, so the solution exists uniformly for all time if this constant here is small. So, and now this constant here, small enough, Cn star here is infinity when n is 1 and 2, meaning we have classical solution in 1 and 2 dimension without any assumption. And we have this assumption when n is greater or equal to 3. So that is our first remark. So here are just some remarks on our result. This is our first remark. Then when m is bigger than 1, what happens if our initials are integrable? When the initial is integrable, kind of same idea. In fact, it becomes easier because here we don't need to multiply by the test function. We just go ahead and multiply by UP. And in this case, the estimate reduces to this. We don't have the bar term. The only problem here is to control this term, we use interpolation. And as such, we cannot have global boundedness because This term can only be controlled by this logistic cells with the L1 norm of U. And L1 norm of U will grow in time. So in the case of integrable initial, we have global existence of weak solution for M bigger than 1, but not boundedness. The bound depend on time. Okay, so let me mention that there have been some studies on other forms of chemotaxis model in the whole of Rn. For instance, the chemotaxis model with linear production, which is the V equation is given by this on the whole of Rn. And ABR 0, that's the minimal chemotaxis model. Now, none of them have studied for non-integrable initial. All the studies were on when the initials are integrable. So in our case, and some of them have restriction on M, so they have global existence under some condition that M is bigger than some number. In our case, we have global existence without any restriction on M and without any restriction on the dimension, which is N, because our model for the case of bounded domain is only studied for when N is 3. And so we don't have the restriction on dimension or the exponent and integrability. And for the uniqueness, most uniqueness result kind of also assumes integrability of initials, and also most of them have some kind of more regularity assumption on like the time derivative of u or the gradient u, which in our case we don't have because because most of this proof follows like a L1 contraction argument, and that's why they needed like the time derivative to be some kind of regular. But in our case, we use like a duality method argument, and we don't have this extra assumption. All right, so for the case of regular diffusion, like I said, we have classical solution. So I want to talk briefly on our first result on asymptotic properties of these solutions for the regular diffusion case. So since we're on the whole of Rn, asymptotic stability depend on the kind of initials. So we can have initials that are strictly positive, initial have compact support, or it's like a wavefront. So it's a question of how does the superlevel set of U propagate in time. So starting from strictly positive initial, our expectation is that the solution actually also is strictly positive, and then we expect it asymptotically as time goes on, it will convert to the steady state solution. So when you look at this equation, we have a steady state solution of U is A over B and V is 0. So we expect that it will converge to that steady state solution, and that is what we first prove. We prove that provided we have a globally defined bounded solution for this chemotaxis model, a solution, if initially the solution is strictly positive, then our U converge asymptotically to A over B, V converge to 0 uniformly in X. Now, let me mention that for some other kind of chemotaxis model, it's not global boundedness does not directly implies that convergence to constant solution. For example, like the linear diffusion case, parabolic elliptic case, some of the work by Salako and Shen in 2017, they have global existence, and then more condition we have asymptotic stability of this constant solution, and then there were study on more steady state solution and like bifurcation in those cases. So one advantage of this is that the V is always bounded, and kind of why we have this. Now for compactly supported initial, we expect that the solution will spread out. And so if you look at our equation without chemotaxis, that's when chi is 0. When chi is 0, the equation reduces to this equation here, which is popularly known as the Fisher-KPP equation due to the work of Fisher, Kolmogorov, Petrovsky, and Piskunov. And what is known of this without chemotaxis is that it has a spreading speed of 2 root A. That is, if you move at a speed bigger than 2 root A, the U goes to 0 in this region, X bigger than CT. And if you move at the speed less than 2 root A, then it goes to A over, it stays positive in this region and converges to A over B. So the question now is, how does chemotaxis sensitivity affect the rate of spread of the mobile species? So naturally, what we expect is that if we have chemo repellent, and we expect that it might slow down the rate of spread. And if we have chemo attractant, we expect that it might speed up the rate of spread in this case. And our first results says, provided we have globally defined bounded solution, usually compactly supported on zero, chemotaxis does not slow down the rate of spread for the system, even when it is chemorepellent. So when you move at the speed less than 2 root A, you convert to A over B in this region, and when U is A over B, looking at the V equation, V goes to 0. So now the question is, does it speed up the rate of spread? So we couldn't answer this affirmatively. So first of all, what we show is that we can get a C star greater or equal to 2 root A, such that for C bigger than this number, the U in this region goes to 0, and when U is 0, you can see the V is like the heat equation. So the V solution is like the solution of the heat equation. Now this says that the chemotaxis does not accelerate the speed to infinity. So the next question is, when is this C star 2 root A? So in general, we don't have an answer to that, but we prove this in some cases. We prove that if V0 is C0 or V0 is an LP for P greater or equal to 1, then it does not slow down nor speed up the rate of spread, meaning the sister up is 2 root A. We already know that it doesn't slow down. And another case we prove is that when U0 is C1 and V0 is C2 plus alpha. So the first case is like, initially, if like far away we don't have the chemical substance, then it does not slow down the rate of it does not speed up the rate of spread. So the second case is like, we're trying to answer when we have this, initially we have the chemical substance everywhere. So like 1 minus V0 is compactly supported. Then we show that we can get a constant such that if chi is negative but not too negative, chi bigger than this number, then it does not speed up in this case. So these are just the cases that we prove, and the proof of this second one is highly non-trivial. We had to like use different things such as the infant soup composition, viscosity solution in order to prove the second equation. And so since we couldn't answer the question affirmatively on whether the chemotaxis actually does speed up the rate of spread in general, we expect kind of like a phase transition, and we give evidence, we only conjecture using a numerical simulation in one dimension that when the sensitivity is large, the chemotaxis might speed up the rate of spread in that case. And when it's small, when the sensitivity is small, then it might not speed up the rate of spread. But this problem is still open in general on whether it does speed up the rate of spread. Okay, so here is like on my current and some future work. Right now, when m is bigger than 1, that is the generic case, we only prove uniqueness under the condition that m is between 1 and 3 for when we have logistic source. So we're still not able to establish whether we have uniqueness without any condition on m. And so that is still open. Okay, so on our model, we would like to study the asymptotic behavior of a solution when m is bigger than 1, also for different kind of initials. So when initial is strictly positive, our equation kind of the Quaternion equation, we expect it will have a classical solution in that case. So what we expect is that the solution should converge also to A over B for U, and V should converge to 0. For the case of compactly supported, even for porous-medium equation, like we have finite propagation, so the solution is, we expect the solution to be compactly supported. And then we have a question on the regularity of, we have like a free boundary in that case, and we want to study like the regularity of the free boundary in that case. So currently I'm looking at this problem, the global existence of weak solution to this Chemotaxis model with linear production. And I think for now we have global existence for m bigger than 2. So the advantage you have for the case of consumption is that the V is always bounded by comparison principle, which was really helpful for us in controlling those terms involving gradient V. But in this case, the V is not always bounded, except when at least locally our opinion of U is bounded. So for now, we have when M is bigger than 2, you have global existence and boundedness of weak solution. But for when M is between 1 and 2, in this case, we have the global existence, but under a condition that B is small, which is the same condition as when M is 1. So we're still working on this problem right now. We'll see what we have. So like I said, this problem has been studied for the case of when we have integrable initial. So we're just studying this for when initial is not necessarily integrable. Um, so our research is supported in part by this NSF grant. Yeah. Okay. Thank you. And yeah, some references.
Thank you for a great talk. Are there questions or comments for Zulaihat?
Hello. Thank you for a very interesting talk. Can I ask a quick question?
Mhm.
So you got in some regime, you got asymptotics, and there's some similarity with the KBB equation. So, but in
Mhm.
KBB, people also do the next order. So the question is, can you do the next order in your model?
Can we do the next order?
Asymptotic.
I'm not sure I know what you mean by the next order.
So like in the case when you have UTX approach AB when t go to infinity, so
Uh-huh.
can you have the next expansion in so UTX equal AB plus something some correction term in small in t.
If I have UT equal to,
So
sorry,
like in the last equation here, right?
okay, yes.
You have the asymptotics in the region of x more than ct. Here you actually approach a over b
A
when
over
t go to
B.
infinity. And
Mhm.
so that's the first term. Can you do like the next term like 1 over t or something like that? So the net order expansion.
Okay. Yeah, I see your question. I've actually not thought about it, and probably, yeah.
Yeah, I mean, there's a log decay term there, right? So you
Yeah, yeah,
have
that's
CT
the
plus the log
function
decay
correction,
term.
something
Yeah,
like that.
right.
Yes. I see. So you mean can we study can we like take limit as t goes to infinity when we have like 1 over t of
Some log correction or something
some log
like that. Like
correction?
yeah.
Yeah.
Yeah, because the speed of propagation is CT, but the next order
Yeah.
term is a log term.
Yeah. Yeah, I think probably, but I've really not thought about it deeply.
Yeah, it would be very interesting. By the
Yeah.
way, I like that picture down there, the one on the right. It looks like an elephant in the Little Prince. Is it? Yeah, I mean, it looks like an elephant. So I like it.
Yeah, it's very similar to in the Little Prince.
Mm,
Yeah, exactly. So it looks interesting.
thank you.
Are there other questions or comments for Zulaihat? Okay, maybe while we are waiting, can I ask you? I got a little bit lost in the bout of the bad terms. I mean, later on when you do
Okay.
the sort of the iterations, scheme. It's very beautiful. I got tiny bit lost here. This is okay. Can you go to the next slide? When you do the, yeah, so when you put it to be delta times the gradient here, the gradient of u of p plus m over 2 times c, and why did this term go away? I just got lost here a tiny bit.
Okay, so we actually divide the diffusion term into two, like
Okay, okay,
diffusion term and use it here.
okay, 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 yeah, okay, I got it, yeah. So it's exactly the exact power, right? Because p
Yes,
plus m minus 2 when you take the
yes,
gradient. Okay,
the
yeah, I
gradient
got
of
it. Okay,
minus two.
okay, yeah, I
So,
got it.
so we still have like this term comes out, but we're able to correct it with,
Sure. Yeah. So then you have to of course the next term with the power q star and 2 over q, whatever that one is still the remnant terms, but the next step when you do the iteration step by
yes,
making it yeah, yeah,
yes,
exactly, that you start with something small, and that's why you only get double the value. Okay,
yes.
yeah, I got it. Okay, yeah, cool. Nice, very nice. Yeah.
Okay.
Are there other questions or comments for Zulaihat in the talk
Just
before we start? Yes, please.
just a curious question. So the cutoff function look very interesting to me. So is it the first time it's appear in your work, or was it have some history before? The cutoff, the joy, the cutoff function.
No, I think to the best of my knowledge, this is like the first time.
Okay.
Yeah.
It appeared in our previous paper.
Yeah, in our previous paper, we only have the decay,
Mm.
Okay.
Mm,
and
yeah.
we needed more property in this case because of that back term.
Uh,
In case of when m equal to 1, just the decay property is enough to like control all the terms.
Okay. So it
Yeah. So
look very
basically,
interesting
it's
to me.
Huh?
right.
It's
Yeah.
very interesting to me.
Okay, yeah, thank you.
Right. But yeah. So okay. Last technical question here. Why don't you make it sort of compactly supported? Why do you let it decay like that?
Um, so let me see. I think for compact, we kind of want like much smoothness property of the test function.
Mm.
And yeah, let me see.
yeah, if it's like this, then we have gradient psi is bounded from above by psi itself.
Yeah,
Mm. Right.
so we
So
want
if it's compactly supported, you cannot have that, right? It's
Uh-huh.
sort of,
Uh-huh.
yeah.
like that,
Okay.
we can have that, so have a problem.
Okay, cool.
Yes.
Okay. Are there other questions or comments you like had? Okay. If not, then let's thank Yulaihat again for a very interesting talk. Um,
Thank you so much for the opportunity to present my work.
Thank you.
Yeah,
So let me stop
thank
recording.